A banking app refuses to launch, not because the device was compromised, not because the user was malicious, but because the operating system was GrapheneOS, an open-source Android fork specifically engineered for hardened security, with a verified boot process, memory-safe defaults, and a minimal attack surface that most stock Android devices cannot match. The Play Integrity API returned a verdict: meets device integrity, false, trust chain broken, access denied. Here is the core contradiction that should stop every security architect cold. The device that was objectively more secure by every measurable technical standard was the one that got blocked. The mechanism designed to enforce trust became the mechanism that punished it. This is not a bug. This is the architecture working exactly as designed, and that is precisely what makes it dangerous. By the end of this lecture, you will understand why this happens at the hardware level, who controls that chain, and how to make architecture decisions that don't blindly inherit someone else's definition of trust. When this story hit Hacker News, it did not generate polite discussion. It scored 19 points, placing it among the highest-ranked security threads in the platform's history. Senior engineers, security researchers, and mobile architects flooded the comments with a single unifying frustration. The system was conflating security enforcement with platform control. But here is what most of those 1909 voters were reacting to emotionally rather than architecturally. The real issue is not GrapheneOS versus Google. The real issue is structural. When a single vendor controls the hardware attestation route, the certificate issuance policy, and the API that app developers are told to trust, you do not have a security standard. You have a monopoly with a security label on it, and that monopoly has direct consequences for your architecture decisions, your enterprise zero-trust policies, and your app's relationship with every device your users might bring to the table. The question is not whether attestation is useful. It absolutely is. The question is, who owns the trust anchor, and what are you actually trusting when you call that API? Let me be specific about what this lecture will equip you to do, because vague security awareness is not what you need. First, you will be able to map the full boot-to-application trust chain from the hardware root of trust, whether that is a TPM 2.0 chip, Apple's Secure Enclave, or a Qualcomm trusted execution environment, all the way up to the API call your application makes at runtime. Second, you will be able to evaluate any attestation API, Play Integrity, Apple Device Check, Microsoft Azure Attestation, and identify its vendor dependency surface, its failure modes, and the architectural risk it introduces into your system. Third, and this is the competency most developers skip, you will be able to apply a structured security versus interoperability framework to make explicit, defensible architecture decisions rather than defaulting to whatever the platform SDK recommends. These are not theoretical skills. Every enterprise zero-trust rollout, every regulated mobile app deployment, and every BIOD policy decision will require exactly this kind of structured reasoning, and the gap between developers who have it and those who don't is widening fast. Here is the architecture of this lecture, and I want you to see it as a single analytical system, not 6 separate topics. We begin at Layer 1, the hardware roots. TPM 2.0 Secure Enclave, Titan M Qualcomm TE. These are the physical trust anchors, and understanding their cryptographic properties is non-negotiable before any higher-level analysis makes sense. Layer 2 is OS-level attestation, how verified boot, DM verity, and key attestation translate hardware trust into software assertions. This is where GrapheneOS lives and where the first structural tension appears. Layer 3 is vendor API structures, Play Integrity, Device Check, SafetyNet's legacy, the abstraction layer that most developers interact with exclusively, and therefore the layer where vendor control is most invisible. Layer 4 brings it all together into policy implications, enterprise deployment, zero-trust architecture, regulatory compliance, and the design patterns that let you work with attestation without being captured by it. By the final chapter, you will have a complete analytical framework and a concrete answer to the question this incident raised. Is there a path that preserves both security integrity and architectural freedom? The answer exists, but it requires understanding every layer before you can use it. Let's start from the ground up, because in the next chapter we go directly to the hardware. Let's establish a precise definition, because most developers misunderstand what hardware attestation actually is, and that misunderstanding is exactly what gets exploited. Hardware attestation is not authentication. It is not encryption. It is a cryptographically signed claim about the state of a device, issued by keys that are burned into hardware at the factory and are physically impossible to extract or replicate in software. Think of it this way. When your server asks a mobile device, are you a legitimate, unmodified device? The device responds not with a password or a certificate you configured, but with a signature generated inside a secure enclave that never exposes its private key to the operating system, to your application, or even to the device owner. The NIST SP 800-193 framework calls this the Platform Firmware Resiliency Model. The integrity claim must originate below the software stack, in silicon. 3 properties define a valid hardware attestation. The key must be hardware-rooted and non-exportable. The measurement must capture actual device state at boot time. and the signature must be verifiable by a remote party without trusting the device's own software. This is the foundational guarantee. But here is the first question worth sitting with. If the key is burned in at the factory, who controls what that key will and will not sign? Now let's confront the core architectural problem that hardware attestation was designed to solve, and why software alone will always fail at this. Imagine you are a bank's backend server. A client app claims it is running on an unmodified, secure device. How do you verify that claim? In a software-only model, the app itself provides the proof. But here is the fundamental flaw. If the device is compromised, if it is rooted, jailbroken, or running a custom OS, then the very software generating that proof is also compromised. It can lie. It can replay a legitimate proof captured from another device. This is the remote attestation problem, and it has been studied since the early 2000s under the Trusted Computing Group's architecture. Software trust assertions are self-referential. A compromised system can always claim to be healthy, because nothing outside the software layer is checking it. Hardware attestation breaks this circular dependency by anchoring the proof in a component that software cannot reach, the secure enclave or TPM. The private key lives there. The measurement happens there. Even root-level OS access cannot forge a signature from that key. The comparison is stark. Software attestation is a witness testifying on their own behalf, while hardware attestation is a tamper-evidence seal applied before the witness even entered the room. But this architectural strength comes with a structural consequence that we will explore in detail, and it is not a technical one. With the definition and the core problem established, let's map where hardware attestation is actually deployed in production today, because the use cases reveal exactly why the stakes of this architecture are so high. First, digital rights management. Streaming platforms like Netflix and Disney Plus use hardware attestation to gate HD and 4K content delivery. If your device cannot produce a valid attestation, you receive downgraded quality regardless of your subscription. Second, mobile payments. Google Pay and Apple Pay require hardware-backed attestation before NFC payment credentials are provisioned to a device. No valid enclave, no payment capability. Third, enterprise MDM enrollment. Zero Trust frameworks mandated by NIST SP 800-217 require device health signals before granting network access, and hardware attestation is increasingly the required signal in Microsoft Intune and VMware Workspace ONE policies. Fourth, App Store integrity gating. This is where developers feel the friction most directly. Google's Play Integrity API and Apple's Device Check Gate app functionality, not just installation based on attestation results. What is important to notice across all four use cases is a pattern. Hardware attestation has migrated from being a security option to being an access control gate. And when the gate is controlled by a single platform vendor, the architecture of trust and the architecture of market power become the same thing. In the next section, trace exactly how we arrived at this concentration. To understand why the attestation landscape is fragmented and vendor-controlled today, we need to trace its origins, because this was not always the design intent. In 1999, a consortium of hardware and software companies, including IBM, HP, Intel, and Microsoft, formed the Trusted Computing Platform Alliance, or TCPA, with a genuinely open goal: define an industry-wide standard for hardware-rooted trust. In 2003, TCPA became the Trusted Computing Group, or TCG, and published the TPM 1.2 specification, the Trusted Platform Module. TPM 1.2 introduced the foundational concepts we still use today: the endorsement key burned at manufacture, platform configuration registers for boot measurement, and remote attestation via the TPM's signing capability. For the first time, a server could cryptographically verify what software was running on a remote PC. TPM 2.0, published in 2014, added algorithm agility, enhanced hierarchy separation, and became mandatory in Windows 11, which made headlines in 2021 when millions of PCs were declared incompatible overnight. But here is the critical observation: TPM was designed as an open, interoperable standard. Any hardware vendor could implement it. Any OS could use it. The trust anchor was the hardware specification, not a platform vendor's proprietary service. This open standard era was the foundation, but it was about to fracture. The arrival of smartphones changed everything, and the industry responded not with standards, but with proprietary solutions. The smartphone era did not extend the open TPM model, it shattered it. And the consequences of that fragmentation are the direct cause of the monopoly dynamics we see today. ARM introduced TrustZone in 2004, a hardware isolation primitive built into the ARM processor architecture itself. TrustZone divides the processor into a normal world and a secure world, a genuinely elegant design. But TrustZone is an architecture primitive, not a complete attestation system. Each vendor builds their own trusted execution environment on top of it. Apple responded by designing the Secure Enclave processor, first introduced in the iPhone 5S in 2013, a completely separate coprocessor with its own boot ROM, AES engine, and key storage. Apple controls the entire stack: the silicon design, the attestation protocol, and the server-side verification infrastructure. Google took a different path. The Titan M chip, introduced in Pixel 2 in 2017, provides a Google-designed security chip for Android's reference hardware. But Android runs on thousands of device models from hundreds of manufacturers, creating a heterogeneous attestation landscape where attestation strength varies dramatically by device. Qualcomm's secure processing unit powers many Android devices outside the Pixel line, adding yet another implementation. The critical architectural consequence. What began as a single interoperable standard in 1999 has become 4 distinct proprietary trust hierarchies, each with different capabilities, different APIs, and, most significantly, different gatekeeping authorities. When you ask who decides if a device is trusted, the answer is no longer a standards body. It is Apple, Google, Qualcomm, or their certified partners. This vendor divergence is not a bug. It reflects rational competitive strategy. But for developers and enterprises building on top of it, it creates a structural dependency that is very difficult to escape. Understanding why hardware attestation became mandatory requires understanding exactly how the previous generation of software-based integrity checking failed in concrete, exploitable ways. Google's SafetyNet API, introduced in 2013, was the dominant Android integrity check for nearly a decade. The premise was simple. The API would evaluate device state and return a signed JSON web token indicating whether the device passed basic integrity checks. The problem is that SafetyNet's basic integrity verdict was evaluated and signed by Google's servers based on signals reported by the device's own software. If the device was rooted, the root itself could intercept those signals before they reached SafetyNet, clean them up, and present a falsely clean report. Tools like Magisk Hide, later renamed Shamiko, automated this bypass so thoroughly that passing SafetyNet on a rooted device became a solved problem with a 5-minute tutorial. Emulator environments could also be patched to pass SafetyNet, enabling automated bot attacks against apps that relied on it for anti-abuse protection. By 2022, Google deprecated SafetyNet entirely and replaced it with the Play Integrity API, which requires hardware-backed attestation for its strongest verdict level. The architectural lesson is unambiguous. When the trust root lives in software, any sufficiently privileged software can subvert it. The attacker who controls the OS controls the integrity report. This is not a failure of implementation. It is a fundamental impossibility result. Software cannot reliably attest to its own trustworthiness. But solving this with hardware created a new set of constraints, and those constraints are what the Hacker News community erupted over. The iOS ecosystem tells a parallel story, and it is equally instructive. Before Apple introduced the Secure Enclave in 2013, iOS device integrity had no hardware anchor. The trust root for iOS security was the signed OS image and the boot chain verification, but once a jailbreak elevated code execution privileges, that chain could be broken. The era from iOS 3 through iOS 7 saw a proliferation of jailbreak tools, Limeran, Red Snow Revasion, that exploited bootloader or kernel vulnerabilities to gain persistent root access. Once jailbroken, an application had no reliable way to detect it, because every detection mechanism ran in the same compromised software environment. Financial applications, enterprise MDM agents, and DRM systems all operated on the assumption of integrity they could not verify. NIST's early mobile security guidelines, including SPA 8412010 from 2010, explicitly flagged this as an unresolved architectural gap. Device compliance assertion without hardware verification was described as administratively asserted posture, not cryptographically verified posture. The Secure Enclave changed this calculus entirely for Apple devices. Keys stored in the enclave cannot be extracted even with a full OS compromise. But the architectural trade-off embedded in that solution is that Apple, and only Apple, controls what the enclave will attest, to whom, and under what policy. We have now established the complete foundation, what hardware attestation is, how it evolved from open standards to proprietary silos, and why prior approaches were genuinely insufficient. In the next chapter, we descend to the actual chain of trust architecture, layer by layer, because understanding each layer is essential to understanding exactly where the control points are and who holds them. Let's start where trust actually begins, not in software, not in the cloud, but at the very first instruction your CPU executes after power on. This is the measured boot sequence, and understanding it is non-negotiable for any architect designing a zero-trust system. Here is how it works. When the platform powers on, the UEFI firmware is the first code to run. Before transferring control to the next stage, it computes a cryptographic hash of that next stage component and extends it into a specific TPM PCR, platform configuration register. Extending means the TPM computes a new PCR value as the hash of the old PCR concatenated with the new measurement. This is irreversible and append-only. PCR captures the core root of trust for measurement, the firmware itself. PCR4 captures the bootloader. PCR8 through 15 capture grub configurations and kernel command lines. Each extension operation is also recorded in the TPM measurement log, giving you a full audit trail of every component that executed. The critical insight here is that no single actor can forge this chain retroactively. The PCR state is a cryptographic commitment to the exact software stack that ran. But here is the question you should be asking. Who decides which PCR values are good? That answer will expose the first structural tension in this architecture. Now let's shift from the PC world to the device in your pocket. Android Verified Boot, or AV2 2.0, implements a conceptually similar chain of trust, but with a structure tailored for mobile constraints and heterogeneous hardware. The architecture centers on a structure called VMeta, a metadata partition that acts as the root of the entire verification graph. The bootloader, which is write-protected and signed by the OEM, verifies the VMeta partition signature first. VMeta then contains cryptographic descriptors, hash trees, and hash references for every downstream partition: boot, system, vendor, and product. For the system partition, Android uses dmverity, a Linux kernel feature that constructs a Merkle hash tree over the entire block device. Any read of a corrupted or tampered block triggers an immediate I/O error before that data reaches user space. The bootloader unlock state is a critical variable in this architecture. When a bootloader is unlocked, the device transitions to an orange verified boot state. This state is recorded permanently, and I mean permanently, in a fuse or a persistent flag that remote attestation services can query. This is not just a UX warning screen. It is a hardware-level signal that travels up the trust chain and into every attestation report that the device will ever generate. Whether that signal should permanently disqualify a device from accessing enterprise resources is a policy question, but the mechanism ensures you cannot hide it. Next, we will see how Apple takes this same concept and builds something architecturally far more opinionated. Apple's boot chain is in a category of its own, and understanding why requires you to think about two parallel trust tracks running simultaneously from the moment you press the power button. Track 1 is the application processor chain. It begins at the hardware boot ROM, mask ROM, physically burned at fabrication, impossible to modify. This boot ROM verifies and loads LLB, the low-level bootloader, which verifies and loads iBoot, which verifies and loads the XNU kernel. Every cryptographic signature in this chain is validated against Apple's root certificate, which means only Apple-signed software can run at each stage. This is by design. Track 2 is the secure enclave processor, the SEP, running its own completely separate operating system called CPOS. The SEP has its own boot ROM, its own private keys that never leave the enclaves, and its own dedicated memory. It is physically isolated from the application processor. These two tracks do not simply run in parallel. They communicate through a hardware-enforced mailbox mechanism with strictly defined message types. When your iPhone performs Face ID or generates an attestation key, that operation happens entirely within the SEP context. The application processor never sees the raw biometric data or the private keys. The architectural implication for attestation is significant. The attestation root of trust is not the device's main CPU. It is the SEP, and that is a hardware boundary that software attacks cannot cross. The question that naturally follows, and we will answer it soon, is what this isolated architecture means for developers who want to integrate with it. With the boot chain established, we now need to understand the hardware modules that anchor these chains cryptographically. Let's start with TPM 2.0, the standard that defines the trust anchor for virtually all enterprise PC and server platforms, and increasingly for embedded and IoT systems. TPM 2.0 is not a monolithic chip anymore. It exists in 3 deployment forms. Discrete TPM is a dedicated security chip on the motherboard, offering the highest tamper resistance. Firmware TPM runs within a trusted execution environment on the main CPU. Intel PTT and AMD FTPM are examples. And software TPM exists purely for testing. It provides no real security guarantees. At the core of TPM 2.0 is the PCR bank structure we saw in the boot chain. 2044 PCR registers per hash algorithm bank supporting SHA-1, SHA-2 to 56, and SHA-384. But TPM 2.0 is much more than a measurement log. It manages a hierarchical key structure with 3 primary hierarchies. The endorsement hierarchy, anchored to the manufacturer-provisioned endorsement, key that proves the device's identity, the storage hierarchy for user-controlled keys, and the platform hierarchy for firmware use. For attestation specifically, the relevant construct is the attestation key, previously called AIK in TPM 1.2, which is certified by the endorsement key and used to sign PCR quotes. This 2-layer key structure is what allows a TPM to prove its identity without revealing the long-term endorsement key to every verifier. Elegant. But the elegance also means the manufacturer's CA sits permanently at the root of every trust chain on every TPM-equipped device worldwide. That is a structural fact worth keeping in mind as we proceed. TPM gives you a discrete measurement anchor, but ARM Trust Zone takes a fundamentally different approach. Instead of a separate chip, it partitions the main CPU itself into 2 worlds using hardware-enforced memory isolation. This is the architecture running on virtually every Android device, most IoT platforms, and many automotive and industrial systems. Trust Zone divides the system into the normal world, where the rich OS like Android or Linux runs with full feature sets, and the secure world where a separate, minimal trusted execution environment operates. This is not a software sandbox. It is a hardware boundary. The CPU has a non-secure bit in its state register, and every memory access, peripheral access, and interrupt is routed based on this bit. The secure monitor, a piece of firmware that runs at the highest privilege level, manages transitions between worlds via a mechanism called the Secure Monitor Call, or SMC. In the secure world, you have the TOS. Common implementations include OPT, Qualcomm QSE, Samsung Kinibi, and Trustonic, and above that, trusted applications, or TAs, which are isolated sandboxes within the secure world. The global platform API standardizes how normal world applications communicate with TAs through a client-server interface. Here is the architectural tension that developers hit in practice. Writing and deploying a trusted application requires OEM or TE vendor approval on most commercial devices. You cannot simply push a TA to a production phone the way you push an APK. That gate and who controls it is precisely what we will examine in the next section on vendor lock-in. Now let's do what every architect should do before committing to a security technology. Compare the actual threat model coverage side by side. TPM, RMT, and Apple's Secure Enclave each represent a different point in the design space, and the differences have major implications for where and how you deploy them. From a physical attack perspective, discrete TPM offers the highest resistance. It is a separate chip with its own power domain, and physical attacks require probing the chip bus, which is detectable and difficult. Firmware TPM running inside Intel SGX or AMD PSP shares silicon with the main CPU, which means a sufficiently advanced physical attacker with CPU decap capabilities has a shorter path to key material. Apple's Secure Enclave, while also on the same die as the application processor on modern A-series chips, uses memory encryption, dedicated buses, and physical separation within the package that places it closer to discrete TPM in practice. For side-channel resistance, think power analysis, timing attacks, electromagnetic emissions. Discrete TPM and Apple's SP have the most hardening because they are purpose-built security processors. ARM Trust Zone is the most exposed here. Spectre-class attacks and catch timing attacks have repeatedly demonstrated that the normal world and secure world share microarchitectural resources in ways that the hardware boundary does not fully protect. From a certification standpoint, TPM 2.0 holds the most rigorous third-party certifications. Common criteria EL4 Plus is typical, and FEPIPS 142 Level 2 or 3 for discrete modules. This matters enormously for government, defense, and regulated enterprise deployments. ARMTE and Apple SCP do not publish equivalent third-party evaluations, is itself an architectural transparency gap. And this transparency gap, who certifies, who audits, who can verify, is exactly the structural issue we are building toward. Hold that thought. We have traced the trust chain from power on through to the hardware security module. Now comes the question that actually matters for your architecture. How does a remote server, the relying party, get cryptographic proof that a specific device is running a specific, unmodified software stack? This is the remote attestation protocol, and it is the mechanism that makes zero-trust architecture actionable at the hardware level. The protocol follows a challenge-response pattern. Step 1. The relying party generates a fresh nonce, a random number used exactly once, and sends it to the device. This prevents replay attacks. An attacker cannot reuse a previously captured attestation report because the nonce will be stale. Step 2. The device's hardware security module, TPM, TE, or Secure Enclave, generates an attestation report. This report contains the current PCR values or equivalent state measurements, device identity claims, and the nonce, all signed with the device's attestation key. Critically, this signing operation happens inside the hardware boundary. The private key never leaves the TPM or enclave. Step 3. The attestation report is delivered to the verifier alongside the certificate chain that links the attestation key up through the endorsement key certificate to the manufacturer's root CA. Step 4. The verifier checks the certificate chain against known good manufacturer roots, validates the nonce, and evaluates the measurement claims against a reference integrity manifest, essentially a policy database of known good PCR values. Step 5. The relying party receives a verification result and makes an access control decision. This 5-step flow is elegant and probably secure under well-defined threat models. But notice what Step 4 requires: a policy database of known good states maintained by or delegated to the vendor. That single dependency is where architectural control concentrates, and that concentration is the subject of our next chapter. On Android, the remote attestation protocol is made accessible to application developers through the Android Key Attestation API, and the mechanism it uses is architecturally clever. Rather than creating a new attestation transport format, it embeds device state claims directly inside a standard X509 certificate as custom extensions. Here is how it works in practice. When your application calls the Android Key Store API to generate a key pair and requests attestation, the Key Store API routes the operation into the TE or Strongbox secure element. The hardware generates the key pair and produces an attestation certificate chain. The leaf certificate, the one for your newly generated key, contains an extension with OID 0.3.1.1.1.1.29.2.117. Inside this extension, encoded in ASN.1, is a structured data structure containing the Android security level, software, TE, or Strongbox, the verified boot state, green, yellow, orange, or RED, the boot patch level, the OS version, and the attestation application ID identifying which app requested the key. The full chain typically has 4 certificates: your key's leaf cert, an intermediate batch cert, a provisioning cert, and the root cert anchored to Google's hardware attestation root CA. Your relying party server parses this chain, validates the signatures, and reads the extension claims. The critical architectural fact: the root of this chain is Google's CA, not the device manufacturer's, not yours. This means Google has the ability to revoke, rotate, or change the semantics of this trust chain. For a developer integrating Android key attestation into a banking app or enterprise MDM system, that dependency is not incidental, it is structural. And structural dependency on a single vendor's CA has a name in security architecture. We will give it that name in the next chapter. Everything we have covered, the boot chain, the hardware modules, the attestation protocol, Android key attestation, these are vendor-specific implementations. TPM uses one protocol, Android uses another, Apple uses yet another. The IETF recognized this fragmentation problem and produced RFC 3334, the RATS architecture, Remote Attestation Procedures. RATS is not a protocol itself. It is an architectural framework that defines the roles, terminology, and trust model that any attestation system should implement. The framework defines 4 primary roles. The attester is the device making claims about its own state, your TPM-equipped laptop, your Android phone. The verifier is the entity that evaluates the attester's evidence against known good reference values. This is typically a cloud service like Google Play Integrity, Apple's attestation service, or an enterprise platform like Microsoft Azure Attestation. The relying party is the service that ultimately makes an access control decision based on the verifier's output, your banking app backend, your VPN gateway. And the endorser provides reference values and endorsements about what a legitimate device state looks like. This is the manufacturer, the OS vendor, the firmware supplier. The architectural insight that RATS makes explicit is this: the verifier role is the concentration point of power in any attestation ecosystem. Whoever operates the verifier controls the definition of trusted. When Google Play Integrity serves as the verifier for Android attestation, Google defines what a trustworthy Android device is. When Apple's attestation service is the verifier for iOS, Apple holds that definition. RATS gives us the vocabulary to name this clearly, and in our next chapter we use that vocabulary to dissect exactly how this verifier concentration becomes the structural mechanism of vendor monopoly. You will not want to miss that analysis. In the previous chapter we traced the trust chain layer by layer, from hardware root keys all the way up to the application layer. Now the critical question is, who controls the verdict at the top of that chain? On Android, that answer is unambiguous: Google. The Play Integrity API is the production-grade successor to SafetyNet, and it issues 3 distinct integrity labels. Meets basic integrity indicates the device passes software-level checks. Meets device integrity means the device is running a Google-certified build with a locked bootloader, and this requires hardware-backed key attestation from a provisioned TE. Meets strong integrity is the highest tier, requiring verified boot with hardware attestation rooted in a factory-provisioned key that has never been exposed. Here is the architectural constraint every developer must understand. None of these verdicts can be obtained without routing through Google Play services. The verdict is not generated locally. It is computed server-side by Google's infrastructure and returned as a signed JGTT token. This means Google is not just a certification authority. Google is the sole runtime arbiter of trust on every Android device that ships with GMS. But this raises a fundamental question. What happens when a device is more secure than stock Android, yet still fails the verdict? The answer will redefine how you think about attestation entirely. Google officially deprecated the SafetyNet Attestation API in 2024, mandating migration to Play Integrity. The architectural shift is more profound than a simple API rename. It represents a deliberate closure of client-side exploitability. Under SafetyNet, the attestation response was a JWS object that could be partially validated client-side, creating attack surfaces for response replay and token substitution. Play Integrity eliminates this by moving verdict decryption entirely server-side. The developer's backend must call Google's Play Integrity API endpoint using OAuth2 credentials, submit the integrity token received from the client, and receive the decrypted verdict JSON in return. This means the plaintext verdict never touches the client device. From a security engineering standpoint, this closes a real attack vector. But from an architectural dependency standpoint, it also means your backend now has a hard runtime dependency on Google's API availability. No Google API call, no verdict, no service. The migration path forces every developer to evaluate this trade-off: tighter security against client tampering at the cost of a mandatory live dependency on Google infrastructure. And the implications go much deeper when we examine who gets excluded entirely from a strong integrity, even when they deserve it most. Here is where the structural paradox becomes undeniable. Strong integrity requires a locked bootloader, full stop. This is not a configurable policy choice by the developer. It is a hard architectural constraint baked into the verdict logic. Now consider GrapheneOS, an Android-based operating system specifically designed for maximum security, with hardened memory allocators, exploit mitigations beyond AOSP, and a verified boot implementation. GrapheneOS devices with a relocked bootloader actually achieve strong integrity. But any device running GrapheneOS with an unlocked bootloader, even during the installation phase before relocking, drops to basic or no integrity verdict. More critically, any custom ROM that cannot relock the bootloader is permanently excluded from a strong integrity, regardless of its actual security architecture. Compare this to a stock Android device with a locked bootloader running unpatched firmware from 18 months ago. That device qualifies for strong integrity. The verdict system is measuring bootloader lock state as a proxy for security, not actual security properties. And this proxy metric is the foundation upon which billion-dollar app access control decisions are made. This is not a minor edge case. It is the structural definition of how attestation monopoly enforces compliance over genuine security outcomes. In the next section, we examine how Apple constructed an even more opaque version of the same problem. Apple's attestation architecture is built on a different philosophical foundation. Rather than exposing explicit device state labels, it provides a cryptographic proof of key authenticity anchored in the secure enclave. The App Attest flow begins when your application calls DC App Attest service attest key on iOS 14 or later. The secure enclave generates a new P256 elliptic curve key pair. The private key never leaves the secure hardware, ever. The application receives a key identifier, which is a SHA-256 hash of the public key. When the app requests attestation, the secure enclave signs a challenge with the private key and constructs a CBR-encoded attestation object. This object contains two critical components: the receipt, which is an Apple-signed blob containing device metadata, and the attestation statement, which includes a certificate chain rooted at Apple's App Attest CA. The developer's server receives this CBOR object and must verify it against Apple's root CA certificate, confirming that the key genuinely lives inside a genuine Apple secure enclave on a genuine Apple device. Key registration is a one-time operation per key per device. Once registered, subsequent assertions use the same key to sign request data, proving that the request originated from the attested app instance. The cryptographic elegance here is real, but the control architecture embedded within it deserves equally careful analysis. Because Apple is the sole CA, Apple is the sole authority that can issue or revoke the trust signal your entire authentication flow depends on. Apple provides two distinct attestation primitives, and conflating them is a common architectural mistake. Device check and App Attest solve fundamentally different problems. Understanding the boundary between them is essential for correct security system design. Device check operates at the device identity layer. It provides two persistent bits of server-side state per device per developer account, stored on Apple's servers. These bits survive app reinstallation and device resets within the same hardware lifecycle. This makes device check the right tool for fraud history signals, for example, flagging a device that has previously abused a promotional offer, even after reinstalling the app. The bits are readable and writable only by your server via Apple's Device Check API, and the device token that grants access to those bits is hardware-bound. App Attest, by contrast, operates at the application key integrity layer. It answers a different question entirely. Is this specific app instance, right now, running on genuine Apple hardware with an uncompromised secure enclave? It provides a per-request cryptographic proof, not persistent state. Use Device Check when you need to remember something about a device across time. Use App Attest when you need to verify the integrity of the current app execution context. Combining both gives you both historical fraud context and real-time integrity assurance, which is the production architecture Apple recommends. But here is where the design tension emerges. Neither API reveals why a device fails attestation, and that opacity is a deliberate architectural choice with significant consequences. This brings us to the most architecturally significant difference between Apple and Google's attestation models, the deliberate opacity of Apple's trust signal. On Android, the Play Integrity API explicitly exposes the reason for verdict degradation. You know if a device failed because of an unlocked bootloader. You know if it failed GMS certification. Can write conditional logic around specific failure modes. Apple's App Attest provides a binary outcome. The attestation either succeeds and produces a valid certificate chain, or it fails. If it fails, the error code tells you the attestation request was invalid, but it does not tell you whether the failure was because the device is jailbroken, because the secure enclave key is compromised, because the device is running virtualized, or because of any other specific condition. Jailbreak detection on iOS is therefore indirect. It is inferred from attestation failure, not explicitly stated. Apple has made a deliberate design choice that the attestation system should not disclose the basis for rejection, which prevents attackers from crafting targeted bypass strategies. But it also prevents developers from implementing nuanced risk-based access control. A researcher cannot study which conditions trigger rejection without empirical testing. A security auditor cannot verify the completeness of Apple's rejection criteria. The secure enclave itself is a black box. Its internal attestation logic is not publicly documented. This is security through opacity, a model that differs fundamentally from the transparency-based trust that frameworks like NIST SP 80190 and FID2 advocate. And as we are about to see, the opacity is not accidental. It is the structural foundation of the monopoly itself. We have now examined both Android and iOS attestation architectures in detail. The natural question for any systems architect is, where does the actual leverage come from? What are the choke points that make this monopoly structurally self-reinforcing rather than a temporary market position? There are precisely 3 choke points, and they operate at different layers of the trust chain. The first is hardware key provisioning at manufacture. When an Android device rolls off the production line, the TE is provisioned with a device-unique attestation key that is certified by Google's root CA. This provisioning happens inside the factory during a process that OEMs access only through Google's certification program. No alternative certification authority has access to this provisioning pipeline. The second choke point is CA certificate chain ownership. Google and Apple each own the root CA certificates that sign device attestation keys. When a developer's server verifies an attestation, it ultimately trusts one of these 2 root CAs. There is no standards-based alternative, unlike TLS, where you can choose from hundreds of trusted CAs or operate your own. The third choke point is the verdict API routing. Even if a device has valid hardware attestation keys, the verdict computation happens on vendor infrastructure. Google computes play integrity verdicts. Apple's servers issue App Attest receipts. The developer is not verifying a certificate locally. They are requesting a verdict from a vendor-controlled endpoint. These 3 choke points are not independently bypassable. They are mutually reinforcing. Disintermediate one and the other 2 still lock you in. But understanding the choke points also reveals exactly where alternative architectures would need to intervene and why none have succeeded yet. The Android ecosystem illustrates how the 3 choke points are contractually enforced, not merely technically dominant. Google Mobile Services, GMS, is the bundle of proprietary Google applications and APIs that most Android users expect. The Play Store, Google Maps, Gmail, and critically, Google Play Services itself. To ship a device with GMS, an OEM must pass the Android compatibility test suite and sign a mobile application distribution agreement with Google. This agreement grants the OEM access to the GMS bundle, but also subjects them to Google's policies regarding what software the device may and may not ship within privileged positions. Critically, the hardware attestation key provisioning pipeline for T keys certified by Google's CA is accessible only to GMS-certified OEMs operating within these agreements. This creates a structural impossibility. An OEM cannot provision Google-rooted attestation keys without GMS certification, and cannot pass play integrity, strong integrity verdicts without Google-rooted attestation keys. The certification and attestation systems are contractually coupled. For enterprises considering alternative Android distributions, LineageOS, CalyxOS, or any AOSP fork, this means that attestation capabilities are not merely a technical matter, they are a licensing matter. The path to hardware-backed attestation trusted by play integrity runs exclusively through Google's commercial certification program. There is no technical workaround because the technical architecture was deliberately designed to be inseparable from the commercial agreement. And the implications for zero-trust architecture, which depends critically on device attestation, are exactly what we examine in the next chapter. We arrive now at the core paradox that this entire chapter has been building toward, and it deserves to be stated with full clarity. Vendor attestation verdicts do not measure security. They measure compliance with vendor certification policies. These are not the same thing, and conflating them is a category error with real consequences. Consider the proxy metric problem formally. A proxy metric is valid only when it reliably correlates with the underlying quantity it is supposed to measure. Bootloader lock state correlates with Google's ability to guarantee the software stack. It does not correlate directly with the actual exploit resistance of the device. Apple's attestation success correlates with the presence of a genuine secure enclave. It does not measure whether the application layer above it is vulnerable. This creates 2 failure modes that NIST's risk management framework explicitly warns against: false positives, where a certified but vulnerable device is granted access it should not have, and false negatives, where a hardened but non-compliant device, like GrapheneOS, is denied access it should have. The industry has built enormous access control infrastructure on a metric that is optimized for vendor ecosystem integrity, not device security integrity. And as zero-trust architecture becomes the dominant enterprise security model, where every device, every request, and every identity must be continuously verified, the quality of the attestation signal becomes the single most critical input to the entire system. What happens when the foundation of zero trust is a commercially motivated proxy metric? That question is precisely what we examine in the next chapter: real-world impact, developers, enterprises, and zero-trust design. Let's start with the decision that keeps mobile security architects up at night. Should your banking app refuse to launch on a rooted device? On the surface, this looks like a clear security win. Regulatory frameworks like PSD2 in Europe and FI guidance in the US push financial institutions towards strong device binding, and FAI2 certification explicitly references platform authenticator integrity as a baseline requirement. But here is the uncomfortable data point. Empirical fraud reduction studies from major fintech players show that device rooting correlates with fraud at roughly 2 to 3% of the blocked population. That means 97% or more of blocked users are security researchers, power users, or enterprise employees running custom firmware, none of whom are the threat model you designed this policy for. The user friction cost is real. Dropout rates of 8 to 15% have been documented at the attestation gate for high-value fintech flows. So the question is not whether to use attestation, it is whether a binary block is the architecturally sound response to a probabilistic signal. That distinction is the entire subject of this section, and it will force you to rethink every gating decision you have ever made. Now let us look at how play integrity is supposed to be integrated, because most production implementations get at least one critical step wrong. The correct flow begins on the client side. Your app generates a one-time nonce, cryptographically binding it to the current session context, typically a hash of the user ID, timestamp, and the specific action being attested. This nonce is sent to the Play Integrity API, which returns a signed JWT, the integrity verdict token, that has been encrypted with Google's key and signed with a Google-managed certificate chain. Here is where most implementations fail. They do not send this token to their own backend for server-side decryption and validation. They trust the client-side result directly, which completely defeats the purpose. On your backend, you must decrypt the token using the Google Play Integrity API server-side SDK, validate the certificate chain back to Google's root, extract the device integrity, app integrity, and account details claims, and critically, verify that the nonce embedded in the token matches the one you issued. If the nonce does not match, you are looking at a replayed token from a different session. Freshness checks, rejecting tokens older than your defined validity window, typically under 60 seconds for high-risk operations, close the replay attack surface. The architecture here is clear. The trust anchor is Google's signing infrastructure, not the device, and not the client app. But wait, what happens when this entire chain depends on Google's API availability? That dependency is a risk most threat models never document. The architectural fix for false positive risk is tiered access design, and it is simpler to implement than most teams assume. Instead of a binary allow or block decision, you map play integrity verdict strength to feature access tiers. A meets strong integrity verdict, hardware-backed, fully verified, grants full access including high-value transactions. A meets device integrity verdict, software verified but not hardware-backed, allows standard features but applies transaction limits or requires step-up authentication for sensitive operations. A meets basic integrity verdict, emulator or side-loaded signature, allows read-only or public content only with a user-facing explanation rather than a silent block. And a failed attestation, which can happen due to Google API outages, not just tampering, should trigger a graceful degradation path, not a crash or a false fraud flag. The checklist here is your implementation gate. Have you defined your tier boundaries before writing any attestation code? Have you built an API unavailability fallback? Have you measured your false positive rate in production? If any of these are missing, you have shipped a policy without an architecture. Next, we move from individual app decisions to the enterprise level, where attestation signals flow into zero-trust policy engines, and the stakes are organizational rather than individual. When enterprises talk about zero trust, they often collapse it into a single question: is this device trusted? But NIST SP 802M7, the definitive zero-trust architecture standard, is architecturally explicit that no single signal is sufficient for an access decision. The standard defines a policy engine that consumes multiple input streams, user identity signals, device health signals, network posture signals, and behavioral analytics, and produces a continuous, risk-scored access decision rather than a session-level binary grant. Hardware attestation is precisely one device health signal in that model. Its role is specific. It answers the question: has this device's firmware and boot chain been tampered with since last enrollment? It does not answer: is this user authorized? Is this network path secure? Or is this behavioral pattern anomalous? Treating attestation as the sole access gate in a zero-trust design is not just technically incomplete, it actively creates a false sense of security. An attested device with a compromised user credential is a fully trusted path for an adversary. The architecture principle here, drawn directly from 802M7, is continuous verification. Attestation signals must be reevaluated access time, not cached from enrollment. Every architecture review board presentation on zero trust should have this diagram and this scene's framing as its opening premise. The two dominant enterprise zero trust platforms, Microsoft Intune with its Windows Health Attestation Service integration and Google BeyondCorp with its device inventory trust model, consume attestation signals in architecturally distinct ways, and the difference has real consequences for how you design your access policy. Intune's model is attestation report driven. The Windows Health Attestation Service generates a hardware health report from TPM measurements, specifically PCR values from the measured boot sequence, and Intune's compliance policy engine evaluates this report against your defined compliance rules. The verdict is binary per policy, compliant or non-compliant. This maps cleanly onto conditional access in Entra ID, but creates coarse-grained risk resolution. BeyondCorp's model is inventory trust level driven. Each device in the Google Enterprise Device Inventory is assigned a trust tier, from unenrolled through managed to corp approved, based on a combination of enrollment state, certificate binding, and ongoing telemetry signals. Access policy in BeyondCorp references these trust levels as first-class policy objects, enabling fine-grained resource-to-trust level mapping. The key architectural insight: Intune's model is push-based attestation reporting, where the device proves its state. BeyondCorp's model is pull-based trust scoring, where the infrastructure continuously reassesses device standing. Neither model is universally superior, but choosing the wrong one for your access policy granularity requirements is a design error that is expensive to refactor. The most politically contentious attestation policy question in enterprise security is the BYOD question. When an employee's personal device has a weaker attestation posture than a corporate-issued device, what exactly should they be allowed to access? The answer cannot be nothing. That destroys BYOD programs entirely, and it cannot be everything. That eliminates the security value of device attestation. The answer is a risk-tiered access table, and you should have it written down before your BYOD program launches, not after your first incident. The table maps two variables: device ownership type, corporate issued versus employee owned, crossed with attestation verdict strengths, hardware-backed strong integrity, software-only integrity, or degraded failed attestation. Corporate devices with strong attestation get full resource access, including crown jewel data stores. Corporate devices with degraded attestation trigger an MDM re-enrollment workflow before access is restored. BYOD devices with software-only integrity get access to collaboration tools and email but are hard-blocked from code repositories, customer PA, and financial systems. BYOD devices with failed or absent attestation get access only to public-facing resources and the IT helpdesk ticketing system. This table is your architectural decision record for BYOD attestation policy, and as we are about to see in the next section, the framework for building it comes from a trade-off analysis that has implications far beyond BYOD. Every architect who has presented an attestation strategy to a leadership team has faced the same challenge. The security team wants maximum attestation enforcement, and the product team wants maximum user reach. Both positions are defensible in isolation and incompatible in combination. The framework that resolves this tension is a two-axis policy decision model. The first axis is threat model severity, ranging from low, where the primary risk is account takeover by opportunistic attackers, to high, where the threat model includes nation-state adversaries, device implants, and supply chain compromise. The second axis is user population diversity, ranging from homogeneous, where all users run corporate-managed devices on known platforms, to heterogeneous, where users span consumer Android, iOS, Linux desktops, and embedded systems without MDM coverage. Mapping these two axes produces four quadrants with distinct policy prescriptions. High threat severity with homogeneous population, enforce strong hardware attestation universally. The CIA triad fully justifies the interoperability costs because you control the population. Low threat severity with heterogeneous population, use attestation as a soft signal for risk scoring, not an access gate. The openness cost of blocking exceeds the security gain. The two mixed quadrants require the most architectural judgment, and this is precisely where most security policies fail. They apply a high-severity, homogeneous policy to a low-severity, heterogeneous population, and wonder why their support tickets are full of locked-out legitimate users. The four-quadrant framework immediately raises the question that vendors prefer you not ask. What do you do when your threat model does not justify full dependency on a single vendor's attestation infrastructure? The answer is vendor-neutral attestation architecture, and it is more mature than most practitioners realize. FID2 and WebAuth and hardware key binding provide a standards-compliant path to hardware-backed authentication without routing every verification through Google Play services or Apple's attestation service. A FID2 authenticator, whether a hardware security key like a YubiKey, or a platform authenticator on a TPM or a secure enclave, generates an attestation statement during credential registration that is verifiable by any FID2 compliant relying party server without calling back to the authenticator vendor. The trust root is the FIDO metadata service, a vendor-neutral aggregator of authenticator certification data maintained by the FIDO Alliance, not Google, not Apple. For enterprise scenarios, open TPM attestation flows using the TPM 2.0 specifications quote mechanism allow any TPM 2 nor equipped device to attest its PCR state to any verifier that holds the device's EK certificate, rooted in the TPM manufacturer's CA. Again, no single platform vendor in the critical path. The IETF RATS Working Group's RFC 193334 architecture formalizes these patterns into a verifier-agnostic attestation framework. These alternatives exist. The question is whether your architectural decision record acknowledges them or defaults to vendor-provided convenience without evaluating the dependency cost. We close this chapter and this analytical framework with the distilled checklist that every architect should run before finalizing any attestation policy decision. First, define your threat model before choosing any attestation mechanism. Not we need security, but Who is the adversary? What is their capability? And what is the asset value at risk? A miscalibrated threat model produces either overblocking legitimate users or underinvesting in controls that actually matter. Second, identify the minimum sufficient trust signal for your specific risk scenario. Hardware attestation is often more trust than you need and less specific than you assume. A phished credential on an attested device is a fully exploited trust assumption. Third, document vendor dependency risk explicitly in your architectural decision record. If your entire trust chain collapses when one vendor's API is unavailable, you have traded a security risk for an availability risk without acknowledging the exchange. These three principles, threat model first, minimum sufficient signal, and explicit dependency risk, are the information management framework that separates architecture from policy theater. In our final chapter, we will synthesize everything into a keyword map of the entire attestation trust chain, identify the open problems that the industry has not yet solved, and tell you exactly what to study next for both the exam and for production systems. The last piece is the one that ties every layer together. Do not miss it. We have now traversed all 5 layers of the hardware attestation trust chain. Let's anchor everything we've covered into a single architectural keyword map, because in information security architecture, if you cannot draw the dependency graph, you do not truly understand the system. At the hardware root, we have TPM 2.0 and Secure Enclave, the immutable anchors that generate cryptographic endorsement keys burned at fabrication time. One layer up, T environments like ARM Trust Zone and Intel TTX execute isolated attestation logic that the host OS cannot tamper with. The remote attestation protocol layer, IETF RATS, Android key attestation, Apple device check, converts hardware-bound key proofs into verifiable claims traveling over the network. And at the apex, vendor API structures, Google Play Integrity, Apple App Attest, translate raw cryptographic attestation into access control policy signals consumed by enterprise-relying parties. Every arrow in this map is also a potential vendor lock-in vector. The architecture is elegant, but the dependency graph is not neutral. Now, the critical question, what happens when one vendor controls every node on this graph simultaneously? Across this entire lecture, 3 structural tensions emerge repeatedly, and they are not accidental friction. They are load-bearing contradictions built into the architecture itself. First, hardware trust versus software flexibility. TPM and Secure Enclave give us cryptographically verifiable device identity, but they do so by making the trust anchor hardware-specific and vendor-controlled. The flexibility that software abstraction normally provides is deliberately constrained. Second, vendor control versus ecosystem openness. Google and Apple do not merely provide attestation infrastructure, they position themselves as the sole authoritative verifiers. No third party can issue an equivalent signal. This is not a technical necessity. It is an architectural choice with market consequences. Third, and most critically, security signal versus actual security outcome. Attestation tells you a device passed a vendor-defined compliance check at a specific moment in time. It does not tell you whether the application logic is secure, whether the user's data is protected, or whether the policy decision is correctly calibrated. Treating attestation as a security outcome rather than a compliance proxy is the trap this lecture was named for. Our architects and developers who internalize these 3 tensions will design zero-trust systems that are genuinely resilient, not just attestation compliant. And this leads us directly to the open problems that even the standards bodies have not yet solved. The attestation ecosystem is not settled science, it is an actively contested standards battlefield. Let's map the live open problems that even NIST, IETFs, and the major vendors have not fully resolved. The most structurally significant effort is IETF RATS, Remote Attestation Procedures. The RATS working group has defined entity attestation tokens, EAT, and concise reference integrity manifest, quorum, as vendor-neutral attestation claim formats. But here is the unsolved problem. RATS defines the message format, not the trust anchor. Each vendor still controls the root signing key. Cross-vendor attestation verification, where a Google-attested device can be verified by an Apple-aware relying party, remains an open interoperability gap. In confidential computing, attestation becomes even more complex. When an Intel TDX trust domain or an AMD SAVVMP virtual machine needs to prove its integrity to a remote workload orchestrator, the attestation chain must traverse firmware, hypervisor, and guest OS boundaries simultaneously. The IETF RATS architecture handles this conceptually through layered evidence, but production-grade implementations remain immature. Meanwhile, the FIDO Alliance's device attestation roadmap, extending FIDO 2 WebAuthn to include hardware-bound device health claims, is attempting to bridge the consumer authentication and enterprise device compliance worlds. The question architects must ask, will FIDO device attestation become the neutral layer we need, or will it simply replicate the vendor API problem at a different abstraction level? That answer is not yet written. Beyond technical standards, regulatory pressure is now the fastest-moving force, reshaping the attestation landscape, and architects who ignore policy vectors will be blindsided by compliance mandates that rewrite their system designs overnight. The EU Cyber Resilience Act, finalized in 2024 and entering enforcement in 2027, introduces mandatory security requirements for products with digital elements. Critically, CRA Article 13 requires manufacturers to document and maintain software and firmware integrity, which creates an implicit regulatory demand for attestable firmware provenance. This is not yet explicit attestation legislation, but the trajectory is clear. In parallel, government root CA attestation frameworks are emerging. The US CISA has begun examining whether federal zero-trust architecture mandates, NIST SP 800-207, should require hardware-attested device identity as a baseline condition for accessing federal systems. If this becomes policy, it instantly creates a procurement requirement that only vendors with FIPS-validated TPM implementations can satisfy, effectively encoding the current vendor duopoly into law. The most disruptive scenario: a government mandates that all devices accessing critical infrastructure must present attestation tokens from a government-operated root CA, not a commercial vendor's CA. This would fracture the current Apple-Google duopoly in a single regulatory stroke. Whether that is liberating or creates new state-controlled choke points is the question every security architect should be modeling today. You have now completed the full architectural analysis of the hardware attestation trust chain, from TPM silicon all the way to regulatory enforcement horizons. But this is not a terminal node in your learning graphs, it is a junction point. 3 adjacent domains now become your highest leverage next study paths. First, confidential computing. Intel TDX, AMD SEVSMP, and ARM CCA extend the attestation model from device identity to workload integrity, proving not just that a device is trusted, but that a specific computation ran and modified inside a hardware-isolated environment. This is the next frontier of zero trust for cloud-native architectures. Second, hardware supply chain attestation. The trust chain does not begin at boot, it begins at fabrication. NIST SP 800-1923 platform firmware resilience and emerging SBOM frameworks are converging on hardware provenance. Can you prove that the chip in your server was not tampered with between the fab and your data center? Third, SBOM-linked firmware provenance. Software Bill of Materials standards, SPT-DXense and CycloneDX, are being extended to include firmware component graphs, creating the possibility of machine-verifiable supply chain attestation from source code commit to deployed silicon. These 3 paths converge on a single architectural North Star, a future where every computation, on every device, in every supply chain node, can produce a cryptographically verifiable integrity proof, and where the governance of those proofs is not monopolized by any single vendor. That future is being built right now in standards bodies, in silicon labs, and in the policy documents being drafted today. The architects who understand the full stack, from hardware root to regulatory framework, will be the ones who design it,